chapter 8.8, which is talking about transition matrices. So this is the last section of this topic. So we'll just get through the notes and then I'll do a video on a couple of more examples. So to start off with transition matrices. So throughout this section we'll be interested in matrices raised to a particular power. For example, m cubed. So we're looking at matrix M. As an example, it might be 1, 2, and 3, 4. And what we're interested in is m cubed. So what we're saying is the matrix M, and we're going to cube it. Oops. Now it's important to note that m cubed actually stands for m times itself 3 times. M times m times m. So we actually get our matrix M times by itself 3 times. And when we do that, we can work out what our answer is by multiplying out the matrix. So this row by this column plus this row by that column, etc., using our train method. And then we get an answer. I'm not sure what we'll get there, but might be 22, 15, 18, and 7 or something. I don't know. Anyway, so that's how we'd work it out. So it's just timesing the first matrix by itself however many times. Now don't fall into trap of doing this. So m cubed, 1, 2, 3, 4. Okay, that's our matrix M, and we're cubing it, so I'll just go put everything to the power of 3 inside. So that doesn't work, so don't do that. Okay, because we have to multiply it out 3 times, and we'll get a completely different answer than what we would get in there. So don't fall in that trap. So don't do this. Okay, and last thing to note is we can only use square numbers, so square matrices. Basically because when you multiply it out, we've got a 2 by 2 and a 2 by 2. And if you remember back from a couple of videos, sections before, these two middle numbers have to be the same. If we had a 2 by 2 and we're multiplying it by a 1 by 2, so a column, a row matrix, okay, these two numbers would be different, which means we can't multiply it out. So it can only be square matrices. The next thing we're going to look at is what's called Markov systems and transition matrices. So Markov system, sometimes it's referred to as a Markov chain, is a system that investigates estimating distribution of states of an event given information about the other current states. So for an example, we're looking at what is the chance of getting rain tomorrow given that it rained today. Okay, so let's say it rained today, the chances of it raining tomorrow might be 70%. Okay, so our initial state, we've got, I'll talk about initial states later on. Our initial state is that it rained today, chances of raining tomorrow is whatever, 70%. Okay, so that's all we're talking about. So just as an example, so we've got a group of delivery trucks transferring goods between two warehouses A and B. They start the day at either warehouse and finish the day parked at one of them. So we've got warehouse A and warehouse B. So assume that at the start of the day, particular truck is at warehouse A. There's a 70% chance that he does his deliveries and then comes back and parks at matrix A, warehouse A that night. So 0.7%, or that's our percent. Now, if we start the day at warehouse B, there's a 60% chance that it will park at B that night. So starting at B in the morning, we end up at B that night, or there's a 60% chance that happens. The other option is that we start at A in the morning and end up at B. So starting at A, end up at B, so 30%, 0.3. And our last option is if we start at B in the morning, what's the probability we ended up parking at A that night? Well, it's going to be 40%, 0.4. Okay, so that's writing the information as a diagram. It might be useful to look at how to do that as a table. So if we started at A in the morning and end up at A, what's the chances of that happening? Well, 0.7, because we start at A, end up at A, there's 70% chance. Well, 70% of the trucks do. If they start at B in the morning, end up at B, we've got 60% of those trucks. And then filling in the blanks, if we start at A, end up at B, we've got 0.3. Start at B, end up at A, 0.4. So I'm just taking that table there, and we could have used the diagram as well. Either one's fine. But what we want to do is convert that information into a matrix, and it's a special matrix, and we're defining it as a transition matrix. So our transition matrix is basically going to be the numbers in this table. So we start at A, end up at A, there's 0.7 of those, 0.4, 0.3 and 0.6. So that's what's called our transition matrix, because it determines from one state to another. So starting at A, what's the chances we end up at A? Well, it's 0.7, etc. So transition matrix. The next thing to look at is what's called the distribution vector and powers of transition matrices. So a distribution vector is a column vector with an entry for each state of the system. So it is often referred to as the initial state matrix, and we denote it by S0. And what it means is our initial state might, for my example before, might be, okay, what's the probability that it rained? It's going to rain tomorrow given that it rained today. Well, let's say it's a 70% chance of raining tomorrow, 30% chance that it doesn't. So rain, not rain. And what we're looking at is, so that's today. And tomorrow is going to be S1. And how do I work out what S1 is? Well, it actually comes from the formula, our transition matrix, times our previous column vector, which in this case is S0. So I haven't defined what my transition matrix is. So today is on the top, and tomorrow is on the side. So what's the chances of it raining tomorrow, given that it rained today? 0.7, 0.3. And what's the chances of it raining tomorrow, given that it didn't rain today? Well, that might be 0.4, which means we've got a 60% chance of it raining tomorrow, or not raining tomorrow. So we can work out what weather it's going to rain or not rain tomorrow. So S1 is going to be our transition matrix times our initial state. Alright, and we work out that whatever answer we get there. So it's probably a good idea to use our CAS. So I'm just going to write in there CAS. Okay. So that means to work out what the next day after that is, I'd do the same calculation, except now I have t times S1. So it's calling upon this this matrix here that we just work out. Okay, and we actually get this recurrence relation. So then S of 3 is going to be our transition matrix times S2, and then so on and so forth. So we can summarize this information. So if I wanted to work out what S of 10 was, well, I can do that by, if we have a look at here, we're multiplying by t each time. So S1, S2, S3. So if I wanted to work out S10, it's going to be my transition matrix, and I'm multiplying it 10 times, so it's going to be t to the n. So if I had t, it would be t to the 10. And then it's just multiplying it by that initial state. So that's a formula that we need to have written down. It's the most important part. And we'll do some practice using those in the next video. Now, steady state is looking at higher and higher powers of t. So the more we do this, so if we want to work out what S of 100 was, we actually get this situation where the numbers in the matrix end up being the same each time because we're getting so high. So we find the values of elements in the transition matrix show no noticeable difference and approach a fixed matrix t to the infinity. And we refer to this as the steady state matrix. And to work out whether a steady state matrix exists or not, we determine a value, so just pick any number. So n is 50 is a good value to test. So I'm going to leave it there, and I'm going to do a couple of video examples in the next video. Thanks for watching.